Hello everyone, my name is Ethan Sprague. I'm a PhD candidate at the University of Michigan in material science, and I studied the material properties of laser 3D printed materials and how 3D printing can be used to create new and exciting microstructures in metals. So, what is 3D printing? 3D printing is a process by which one takes a design in their computer and a program will take that design and cut it up into a series of smaller pieces and then design a toolpath to deposit the material until the final structure is formed. This is different than traditional or subtractive manufacturing, where an entire block of material will be present and then the resulting shape would be cut out. This process eliminates a significant amount of waste, and also it eliminates a significant number of steps required to go from the design process to the actual finished part. This technique is rather mature, especially with plastics, but in order for it to be used in a lot more real-world situations, we need to make a transition from plastics to metals. With plastics, you can use a filament and a heated nozzle to deposit your 3D printed structure. But with metals, you need to use something a little bit different. With metals, we use powdered metals, and we focus a stream of powder underneath the laser, and we draw the nozzle around in the same way we would with a plastic one to make whatever shape we wanted to make. In practice, that looks something like this, where the laser goes down through the column of powder and collects and deposits a thin layer of material. Those layers can be stacked on top of each other, as is being shown right now, to make basically any shape you want to. In order to understand what the resulting materials look like, we need to understand what an alloy is. Pure metals arrange themselves into crystals, which are just atoms arranged in a repeating pattern. This pattern can be made up of repeating cubes, hexagons, or any rhombohedron. In iron, the atoms arrange themselves into a cubic structure, similar to what is shown here. An alloy, on the other hand, requires two different metals to form. It can form in three main ways. First, we can get substitutional alloys, which is where atoms can be switched out without significantly affecting the crystal structure. A common substitutional alloy is bronze, where the hexagonal pattern of the copper atoms is not changed by the addition of tin atoms. Another type of alloy is the interstitial alloy, where atoms from a smaller element sit in the spaces between the larger metal atoms in the crystal. An example of this would be steel, where the iron atoms continue to form a cubic structure and the carbon fits in the gaps in the crystal. Finally, we have immiscible alloys, where the two elements do not like mixing at the atomic level. Rather than a truly mixed metal, there are regions which are purely one element or another. An example of this is copper mixed with a body-centered cubic metal like iron. This is the material we are attempting to make through laser 3D printing. The key takeaway here is this: immiscible alloys don't like to mix, just like oil and water. Just because these metals don't like to mix as solids doesn't mean they don't like to mix as liquids. And because laser additive manufacturing has a nifty property of incredibly high cooling rates, we were wondering if these super high cooling rates would actually freeze the copper and iron together in a new novel alloyed structure which we had never seen before. Looking at the microstructure of these samples after we printed them, we saw that there was still separation between the copper and the iron, with the copper here being shown as the lighter phase and that darker phase being the iron in between. It appears then that we weren't successful in actually getting these two elements to mix at the atomic level, even though we have a very fine mixing at the microscopic level. If we zoom even closer in, though, we start to see something very interesting, that within the iron-rich regions, we have these light dots, which appear to be made out of pure copper. And within the copper region, we seem to have these dark regions, which seem to be made out of pure iron. This is counterintuitive because these two metals should try to separate as much as possible, but even within the seemingly pure iron phase, we were able to capture some copper, and within this seemingly pure copper phase, we were able to capture some iron. When we actually look at the atomic arrangement in these little regions, we see that it appears that we're getting hexagonal regions of iron within this hexagonal copper, and maybe even some cubic regions of copper within the larger cubic iron. So within the microstructure, there is an even more complicated nanostructure embedded at an even deeper level. And so we are very excited with these early results, and we're continuing to study how these nano precipitates are affecting our mechanical properties. The takeaway here is this. Not only can additive manufacturing create new shapes and new structures that don't require months of background design or tooling in order to make, but they also allow us to create new and interesting material properties that we wouldn't be able to get with other manufacturing techniques like casting. And so this shows that 3D printing is as much a material science problem as it is a mechanical engineering problem and a design problem. And that opens up this entire field to be studied for a wide range of materials and to see how this laser process affects the final resulting strength and durability of these structures. Thank you very much for listening.